Alrighty. So, today we're going to be talking about section 2.3, which we're still in chapter 2, so we're still talking about limits pretty exclusively. And in fact, today we're going to learn about all the limit laws. These are going to be pretty important to remember, if only because a lot of the things we'll be talking about later are going to have the exact same laws, because they're going to be secretly, hiddenly also limits. So they're not always going to work exactly the same. So we also need to be able to contrast the multiple different types of laws we'll be getting. But this is our first sort of list, and there's a lot to compare as well. So for all of these laws, we're going to presume that the limit as x approaches some constant c of f of x, we're going to call that capital F, and that the limit as x approaches that same constant c of the function g of x exists and is equal to some capital G, right? And we want to note f nor g can be equal to infinity, right? So I mentioned this last section that we can say that the limit is equal to infinity, right? We have meaning for that. That was part of our definition. But for the case of these laws, the limit equaling infinity doesn't let us work with it. It doesn't guarantee all the things that we're going to come across next, right? So what we want to have is two functions whose limit we can find out, and it's a number, not infinity, right? And with that in mind, we have the sum rule, which says that if we're taking the limit as x goes to that same constant as before of the sum of two functions, well, that's just going to be the sum of the limits, right? So in other words, we can break limits up on sums, right? We have the product rule for limits, and that's the limit as x goes to that same constant of f of x times g of x is going to be equal to capital F times capital G. We have the constant multiple law. And that says if we have the limit as x goes to some constant c of a constant k times f of x, that's just going to be that constant k times f, right? And in all these times, whenever we say constant when we're talking about a limit, we mean anything that doesn't have the variable in it, right? Remember from our notation from last time, the variable is whatever's here, right? So if I said the limit as y goes to c of f of x, that's just going to be f of x again. It's not even going to be capital F because of the constant rule that we talked about last time, right? So this constant k can be anything in the world as long as it doesn't have any x's in it. So we have a quotient law, which says the limit as x goes to c of f of x divided by g of x is going to be capital F divided by g. This one has a little caveat, which you might be able to guess, and that is we can't divide by 0, at least not in the standard algebraic way. So if g is equal to 0, then this is not going to be equal to f divided by g because that doesn't mean anything by itself. And the last one, the book splits this up in a couple ways, but I'm going to try and be efficient with my writing it down. So if we have, again, limit going to that same constant of our function being raised to a power, right? So here y can be any sort of number whatsoever. That's going to be that limit raised to the yth power, right? So that works for if y is a constant, right? If we're looking at g of x squared, if we're looking at g of x to the fourth, or it works for roots, right? So just as a reminder, this might be something that has slipped in the back of your mind. The square root of something is that something raised to the 1/2 power, right? So if that something in this case was g of x, then y in that case would be 1/2. And so those are all our rules, right? And that's pretty much what the entirety of this section is about. So we're going to get to doing some problems. Right. So let's do the limit as t goes to 1 of the square root of 2t plus 7 all over t minus 3 cubed. All right, so one of the things as you do problems like this is that you're not necessarily going to know this from the very start, right? Because you're going to start off with something that's all combined and combobulated, right? So maybe you don't know that the limits of the individual pieces exist yet, right? But that's where we have to be careful. We're always going to do the same process, but if we get down to a point where we figure out, oh, hey, one of these limits doesn't exist, or, oh, hey, turns out the denominator was equal to 0, then we stop, right? And we say that, okay, we haven't disproven anything, we just don't know what's going on, right? So it doesn't tell you that the limit doesn't exist, it doesn't tell you what the limit is, it just tells you that you're going to need some different tools for it, right? So we're going to break this up, kind of doing PEMDAS, right? Parentheses, exponents, multiplication, division, addition, and subtraction, with the one caveat that a lot of folks forget, that is, anytime you see a fraction, there are hidden parentheses, right? We don't ever draw them like that because the fraction line does it for us, separates it into two pieces. But when we're thinking about PEMDAS, we've got to look at fractions and recognize that there is a hidden set of parentheses there, right? So first we're going to use the quotient rule to say that this is going to be the limit as t goes to 1 of the square root of 2t plus 7 all over the limit as t goes to 1 of t minus 3 cubed. Yep. And so that was our first parentheses, right? Next would be exponents. And we use this root rule here to know that this is going to be the limit as t goes to 1 of 2t plus 7 raised to the 1/2, right? We can take the thing inside the limit, right? Really, there maybe should have been that there, and put it on the outside of the limit. And then the limit as t goes to 1 of t minus 3, and put that 3 out there. And then we can finally get to addition, right? So we've got the limit as t goes to 1 of 2t plus the limit as t goes to 1 of 7. All of that's going to be rooted. And then we have the limit as t goes to 1 of t minus the limit as t goes to 1 of 3. And all of that's going to be cubed. And let's see. Whoops, I forgot to write. This is using the power rule. This is using the sum rule. And I did sort of cheat a little bit in there, right? We calling this the sum rule, but we let ourselves break up differences as well. That's technically combining the sum rule with the constant multiple rule, right? Because subtracting is just adding a negative number. So we're saying that that's really t plus negative 3, right? And so we split that up as a sum, and then we pull that negative constant multiple out. But we can also just think of it as the sum and difference rule and know that we can break up on differences. Right? So now we do need to use the constant multiple rule. Why I spread it out like that, to get 2 times the limit t goes to 1 plus the limit t goes to 1 of 7, the limit as t goes to 1 of t minus the limit as t goes to 1 of 3, right? And this is to the 1/2, and this is cubed. And now our last step for any of these is always going to be those two rules that we learned last section. I don't remember if we gave it a name. I'm going to check and see what the book calls it. If it calls it something, it might not call it something. It doesn't. It doesn't give it a name. But it's the one that says that the limit of a constant is just that constant, and the limit of the variable is whatever c is. Right? So in this case, when t is going to 1, t is going to 1, so that's 2 times 1. When t is going to 1, 7's not changing, so that's 7. When t is going to 1, t is going to 1. And when t is going to 1, 3 is not changing. Right, and finally, some algebra. And some labels so that we can follow along. We get 3 over negative 8. Whew. So, I'm going to do this same problem slightly differently. And by slightly different, I mean very differently. And I'm going to make the claim that the second way is not only a hell of a lot easier, but it's really what our rules are telling us we can do. Right? So if I just take all of my t's rather, and replace them with 1, we'll notice that I got to this step a hell of a lot easier. Right? So I'm just going to go ahead and do the algebra real quick. So this is called substituting. And it features into what we're going to do next section a whole lot. Right? Next section is actually going to be about when we can substitute. Right? But even just having these limit laws right here, we know that we can do it for any function involving sums and quotients of sums of power functions. Right, if you recall, a power function is something that looks like this, right? So power functions we know we can do because we have the constant multiple rule and we have the power rule, right? Sums we can do because we have the sum rule, and quotients we can do because we have the quotient rule. And technically we don't need to use product rule for anything like this. But something to be careful of, we can't, now that I've said that this is substituting and you can do it in these cases, right? As we go, we're going to build up more and more functions that we're allowed to substitute in, right? Technically, the overarching class is continuous functions, which is a definition we're going to get into next section. But for now, we know that these types of functions are continuous, right? And we don't have anything that tells us that other types of functions are yet, right? So for now, we have the rule that we can substitute just fine using our basic limit laws, as long as it is a function involving sums and quotients of power functions. That pretty much covers all the problems that if we can solve it using just what we have so far, it's going to be something looking like this. I do want to do one problem where it looks like we could do it, but we have to be careful. Right, and we can sort of get there the same way. Right, and again, doing this the long way just because I know a problem's going to come out of it, and then we'll talk about the short way. Right, we would break this up using the quotient rule. All right, and looking at that, I can see right off the bat that I don't even have to worry about what's up here, because this guy is definitely going to 0. Right? If x is going towards 1, 1 minus x is getting closer and closer to 0. Right? And so that tells me that the fact that I use quotient rule here is no good, because quotient rule says that it only works if the limit of the denominator is not equal to 0. Right? So when we're doing something like this, the limit of the denominator is not equal to 0, so we can't use the quotient rule. Right? And we could have gotten this the exact same way if instead we'd done substitution. We would get the cube root of 1 plus 5 all over 1 minus 1 equals the cube root of 6 over 0, and this is bad. Right? And technically we don't have any tools to deal with this yet. It doesn't mean, just because we got that 0 on the bottom, that by itself doesn't mean that the limit doesn't exist. In fact, this limit I know goes to positive infinity. But just looking at that 0 right there doesn't tell me that. Right? If you get a 0 on the bottom, you can't use the quotient rule. You have to use something else. You have to use something else to help you find an answer to it yet. And we don't have that something else quite yet. I think we'll get it in 2 sections. Yeah, I think we talk about it in, 3 sections. Nope, 2 sections. 2.5 is when we talk about it. Now that I've learned to read a little bit. Right, so just to do one more problem to have that practice with it. Right, so if we have the limit as z goes to -2 of the fourth root of z plus 18. You can put parentheses in there, but it's not standard practice, so I don't want to confuse folks with it. All right. Yeah. So this is a function that is made up of power functions and then the sum or difference of them and then more powers of that, right? So looking at it, and then a quotient, of course. Looking at it, I can see that all of our rules say that I can do substitution here, right? So I can do that this is the fourth root, right? And I'm going to put a question mark there because I need to know that they both exist and that the bottom's not equal to 0 first. And so we get the fourth root of 16 all over 2 minus negative 6. So the fourth root of 16, remember that means we need to cancel out a fourth power, right? So if we realize that 16 equals 2 to the fourth, then we can figure out that the fourth root of 2 to the fourth is 2. Oops. I don't know where that, well, I guess I was skipping ahead to get that 8. The fourth root of 2 to the fourth is 2. 2 plus 6 is 8. And then we always want to try to have our fraction with the lowest possible denominator. Alrighty. So for the most part, we're going to keep coming back to these limit laws. They continue to be true even as we learn about different sorts of functions that we can deal with them. And as we go through each section, we're going to add on to our sort of library of functions that we can just do substitution with. Right? It's going to turn out that most functions that we look at, we can probably do substitutions. I'm actually going to go through and finish some things up because we figured out that this substitution doesn't work because we have a 0 on the bottom, and this substitution does work because we don't have a 0 on the bottom. Right? So next time we're going to actually talk about what that idea of continuity means. And figure out some vocabulary related to it. So I will talk to y'all then.